Good evening, everyone, and welcome to the last Café Scientifique before the summer break. We will be back in September, but yeah, so last one for the term, as we say, university, and it's an honor to introduce today's speaker, Heather Russell. Heather is a faculty member at the University of Victoria since 2021. And in the physics department, where she studies the smallest particles in the universe, which she's going to tell you about today. And she also does many important things for the department. For example, she's the chair of the committee looking into equity, diversity, and inclusion. And she's studying this tiniest particles, part of the ATLAS collaboration at CERN since 2012. So she also used to be there as a senior research fellow. And before that, she was a postdoctoral fellow at McGill University And yeah, so the interesting thing is today we have an actual musician here. So Heather is actually a musician, which kind of is a great fit for the jazz club, I think. And okay, just to make here a little bit of an advertisement, I'm not sure if everybody here is aware of that we also do concerts at the University of Victoria. And in fact, if you have no plans for May the 3rd, then Heather will be performing with the Victoria Choral Society, and they will perform Beethoven's Ninth. Freude, schöner Götterfunken. Something like that. I can speak German, I can't sing. Okay. Yeah, anyhow, so yeah, there will be the Victoria Choral Society together with the Victoria Chamber Orchestra. And I think this is all. Heather will tell a little bit about herself in the beginning of her talk. She's actually from the island. Yeah, so Heather, please take it away.
Thanks for the introduction. And thanks everyone for coming tonight. This is awesome. I have to get myself set up and remember who I am. All right, so yeah, as Toby said, I was going to talk a little bit about myself first. So I'll start right from the very beginning. Now, when I was a child, my class did a unit on space. You know, the sun, planets, stars. We all got to create a really big list of all the things we wanted to learn, what our questions were. How many planets are there? How big is the sun? Pluto will always be with us, right? But I wanted to know, what does it mean for the universe to be infinite? And if it isn't infinite, what does exactly it mean for it to end? I always sort of pictured a brick wall solid way off at the edge of space, and brick walls always have another side. I was a very literal child. But as I went on in school, I started to realize just how many unanswered questions there really are about the universe. Not just its size, but what it's also made of at the smallest scales. And how we got from that singularity at the very start of the Big Bang to the matter that makes us up today. In an ongoing attempt to answer these questions, I became an experimental particle physicist and a member of the ATLAS collaboration at CERN. But we can go back a little. So I'm originally from the Cowichan Valley, so if any of you happen to know Mrs. Carter, who taught at Maple Bay Elementary in the early 90s, I can tell her I'm still trying to answer that question, but I'll let her know if I find a solution. But I did all my schooling in Cowichan Valley in the public school system. I really liked math. But at 16, I didn't really understand how math translated to a career. And I was also completely useless at memorizing anything, which is why I have what I'm saying down here. So I dropped biology, that wasn't an option. And physics really seemed like a good compromise. It was math, but with some well-defined physical purpose. So I did my undergraduate degree at UVic. I worked for a year at what's now Brooks West Shore in Langford. And then I carried on my mission to understand the universe with math, with a master's degree at the Perimeter Institute for Theoretical Physics. That's in Waterloo in Ontario. I then started a PhD at the University of Washington in Seattle. I had enough of the East Coast after about 10 whole months. And that was to study physics education. That's researching how to teach physics at the undergraduate level. Okay, so you're thinking you're now years and years into graduate school and we're still not talking about particle physics. So I'll get there. For various important reasons, like there wasn't very much math in education research, I eventually found a home in the ATLAS group, and that's where I started my particle physics journey. I kind of hesitated to tell this roundabout story because I think it often contradicts the image of what we have in our minds that are here about scientists. That's someone who has always known what they wanted to do and had that in mind as I'm going to become a physicist and solve all the problems in the universe. But I think it's also important to hear other stories. You don't necessarily have to have a set path in life, and that's okay. So basically, my question about the universe was the only one we didn't answer in that space unit, and I'm still doing my best today to understand how the universe works. So I mentioned at the start that I do my research as a member of the ATLAS collaboration at CERN, and we're going to unpack what that means, starting with CERN. So CERN stands for the Conseil Européen pour la Recherche Nucléaire. That's the European Organization for Nuclear Research. It was founded just post-World War II as a place for countries to collaborate peacefully on projects that were increasingly large and required like big international collaborations to fund and build. Now, as suggested by the name, CERN's original purpose was nuclear physics. It just really didn't take long for physicists to realize that there was something inside of those nuclei, a shift that really took CERN from nuclear physics into the growing field of particle physics. Now, we haven't always had large collaborations at CERN. It just gradually sort of happened over time. First, you needed another couple people to come help build your detector and run your experiment, and then a few more, and then a few more. And at one point, I actually thought this was really interesting, the evolution of small science experiments, tabletop physics, we call it, to the giant collaborations we have today. And I thought, I'll compile a list of the historical collaboration sizes at CERN. But if you go back far enough, there was just tons of these tiny little groups that popped up and out of existence, and it became far too much to track just for fun. But it really did sort of happen gradually over time. Now, CERN's role in this is to provide the facilities, right? The facilities necessary to carry out the scientific goals of the experiments that really the funding institutions are willing to fund. Now, over the years, they've sort of been novel research advances that have come out of this. Not the science itself, but out of the facilities we need to do our science. For instance, Tim Berners-Lee is a physicist, was working in the computing division at CERN and realized that if our experiments were going to continue to grow as planned, the LHC at that point was on the horizon, and they were growing not just in numbers of people and amount of data, but also geographically, the spread of the countries involved. And if that was going to continue to happen, we needed a way to share information between different networks, different computers, and different countries. So he invented the World Wide Web as a solution. The initial feedback on his work was vague, but interesting. And luckily, or not, you can decide, he was provided the resources to develop his idea. And here we are today, thanks in part to international scientific collaboration. Now, over the past 50 years, as the complexity of our experiments has grown, we've gone from our big experiments with a couple hundred people running for a little under a decade, it sounds big, right? To where we are today. My collaboration, there are nearly 3,000 authors. We call 3,000 people who are qualified to be authors on our papers, and around 6,000 total members. And we're on our 15th year of data taking with 15 more planned. So this gradual growth, right, of collaboration sizes sort of organically over time has given us as a field, and many people have gone from collaboration to collaboration throughout the course of their career, given us a lot of time to sort out how we'd work together within collaborations, right? How should they be structured for maximum efficiency? And how do we make sure that there's people working on even the least interesting tasks that are often sometimes the most necessary ones? And I always think it's really too bad we didn't spend more time figuring that out. But I want to talk a little bit now about the research we're doing at CERN today with ATLAS and the Large Hadron Collider. And in order to do that, I need to give you all a crash course in the standard model of particle physics. Okay, so the matter that makes up you, me, the stage, right? This is made up of atoms and molecules, right? Inside the atoms, we have electrons, and at the center of the atom, we have a nucleus. So it's a dense nucleus of neutrons and protons. We only actually learned that fact less than 100 years ago. So we're not talking about a huge amount of time to understand the universe yet. Protons and neutrons inside the nucleus are made up of fundamental particles called quarks. Protons are made up of 2 up quarks and a down quark. Neutrons are 2 down quarks and an up quark. Now there's nothing literally up or down here, right? This is just a label. We could have easily called them like quark A and quark B, but that would be really boring. The key thing here is that they're different types of particles, okay? They're actually different. Now, as far as we know, and we have been wrong about this many times before, electrons and quarks are what we call fundamental particles. They're fundamental because unless you're a string theorist, we don't think there's anything inside of them. You can't look in further, that's it. That is the tiniest building block of the universe. But you've probably heard of some other particles, right? Probably the Higgs boson, for example. And we're going to talk about that a bit later, but first I want to discuss the photon. So who's heard of the photon? About half. How many actually know what a photon is? I see my husband there, sort of shaking his head, and we're gonna have a talk later. But so don't worry, it's not a test. If you do want one, my class's exam is on the 24th, and I can give you the details. It's about modern physics, so this is relevant. But a photon. So photons, use this yellow foam ball as a photon. It's a quanta of light. That is a discrete piece of light. A particle, right? It's a particle. In certain situations, we cannot use what we call the wave model for light, electromagnetic radiation, because that does not fit our experimental observations. What does fit them is a particle model. This leap, that light can come in discrete particles, was what Einstein got the Nobel Prize for. So this isn't like an obvious thing I'm expecting you to all just figure out or anything. Okay, so that's a photon. Now let's consider an electron. Everywhere around it, around us, everywhere, is an electromagnetic field. This electron affects the field at every point in space. Okay? And at every point in space around this electron, there is an electric field that points towards the electron. That's the direction that something with positive charge would travel. So if I had a positively charged proton, it's attracted towards the negatively charged electron, right? And the farther you get away from the electron, the weaker that attraction is. That's the weaker the electric field gets. This field we call a vector field because it has both direction and magnitude, amount of strength. Now, can't see the colors here. Yeah, green. Okay, if we put a second charged particle into this field, the charges are going to be either attracted or repelled, depending on what they are. Now, I've pulled up two green ones. You can think maybe they're the same. These are two electrons, believe me. And they'll be attracted and repelled just like magnets would, right? Now, two electrons will repel each other because they have the same charge. Then the question is, how do they get that message to each other? Like, hey, we'd better stay away from each other? No, I mean, they're not talking to each other. The thing they do is they actually interact, they affect the same electromagnetic field. And they do that through exchanging photons back and forth. It's a bit of a funny thing to think about, like they're not like throwing particles back and forth. So there's an analogy we like to use here. So you can imagine that you and a friend are off to play a game of hockey. You get on the ice, but realize that you've got a basketball instead of a puck. If you pass the ball to your friend on the ice, right, you're going to move backwards. And as your friend catches it, they're also going to move backwards. So if you go back and forth, you repeat that, you're going to end up farther and farther and farther apart. You're the electrons, and the basketball is the photon being passed back and forth. The photons, we call the particles that mediate the electromagnetic interaction. This electromagnetic interaction is what keeps electrons bound into our positively charged nucleus. So we can think a little bit deeper about that nucleus. Let's say the nucleus of a helium atom. Okay. So a helium atom is an alpha particle. It has 2 protons and 2 neutrons in its nucleus. I can't hold 2 protons and 2 neutrons in my hand, so we're just going to do the proton part. These are 2 positive charges, right? And what we know about the electromagnetic interaction is they're going to be repelled. So something else has to be overcoming this force, right? Otherwise, we wouldn't have a nucleus. They wouldn't be held together, but we know the nucleus stays together. And that thing that holds it together we call the strong force, because it's kind of strong. And it's also what holds the quarks inside the protons and neutrons together. Now, the strong force is what we call a very short-range force, meaning it only works over tiny distances, around the scale of the nucleus itself. This is kind of different from, for instance, the gravitational force, which we can feel the effects of the sun on the Earth, right? It's pretty long range. But here, the strong force is only acting on a nuclear scale. And this is actually, it seems a bit funny, but it's because it's so strong that it's confined to this really tiny scale. Now, like we had a mediator photon for the electromagnetic force, for the strong force, we also have a mediator, and we call this the gluon, because it's literally the glue that holds us all together. Now, if you're keeping count, I think we're up to 5 particles now. We have up quarks, down quarks, electrons, photons, and gluons. Yeah, 5. Now, through experiments over the past century, we've discovered many other fundamental particles. There are actually 6 quarks, up, down, charm, strange, I always get those two mixed up, top and bottom. There are 3 leptons, electrons, muons, which you might know from cosmic rays, and the tau lepton. There's a neutrino associated to each of the leptons. There's the photon, the gluon. There are 3 mediators of the weak force. We call these W and Z bosons. The weak force is what's responsible for nuclear decay, like beta decay. And lastly, there's the Higgs boson. And this is what we need in order for all of the other particles in the Standard Model to have mass. And they are massive particles, so it's a good thing the Higgs boson exists, or we wouldn't be able to actually explain this. Now, the Standard Model itself is a mathematical model that describes all these known particles and their interactions. The key word here is known, right? That's doing a lot of heavy lifting. Once we know something, we can then modify the Standard Model to accommodate it. But until we know for sure, the Standard Model has to stay as is. So, for example, if my colleagues discovered a dark matter particle tomorrow, that doesn't mean we have to throw out the Standard Model, just because it's not there. We have to just modify the Standard Model to include that particle. It is possible that we would discover something that means we have to throw the Standard Model completely out the window. And I think, honestly, as scientists, we have to be open to this. But probably that's sort of unlikely at this point. The neat thing about the Standard Model, though, is also that it's a predictive model. When it was put together, with the particles that we knew at the time, the only way the math worked out is if there were those W and Z bosons I mentioned earlier. But they hadn't been discovered yet. So when they were subsequently discovered in the early 1980s, this was a great success for the Standard Model. So if these hadn't existed, then it really would have been, I think, back to the drawing board for the theorists who were proponents of this model. Now, the Higgs boson, the particle that can give everything else mass, is absolutely critical, I think, to our formulation of the Standard Model. And its discovery was the main goal of the Large Hadron Collider and the experiments using it to do their physics. We achieved this discovery in 2012, about a month before I started my own particle physics research career. This is a coincidence. I have to admit I really didn't understand all of the fanfare at the time. I do now. And so it's tempting to think that 2012, it's been like ages since, what are we doing, right? At this point, we've achieved our mission, the Standard Model is done, and why on earth are we still going? Someone actually asked me this in an interview once. Has the LHC discovered anything since the Higgs? And it turned out this was more of a rhetorical question. I did not get that job. But it's also, I think, a completely valid thing to ask. It's a valid question to have, something some of you might have. Why are we still going? So I think, first off, knowing a particle exists is like the bare minimum. So since the Higgs discovery, we've been studying how the Higgs boson interacts and decays, how all of the other particles in the Standard Model behave and interact. We've also discovered 77 other particles, not fundamental particles like the Higgs boson, ones that can be broken up into pieces, ones made of quarks called hadrons. And these are particles kind of like protons, but different. When the quark was originally introduced in the 1960s, the theorist who proposed it, as Murray Gell-Mann, postulated that you could also have hadrons with 4 quarks or 5 quarks. And this is something that's only really in the past few decades that we've been discovering. We call them now tetraquarks or pentaquarks. They've got really great descriptive names like ZC 3900 and PC plus 4380. Not quite as fun as the Higgs boson. There's a lot of these, 77, they're not all pentaquarks, but 77 new hadrons we've discovered. And this is all well and good, but for many of us, right, this doesn't answer the question of what is going on in the universe, right? We want to answer some very basic questions about our existence. The first off, what is this dark matter stuff that makes up like 85% of the matter in our universe? That's a lot. I mean, if I told you I know 15% of what's in your drink and the remaining 85% was a mystery, you'd be a bit disturbed, right? I would be. But I think the other issue I find is even worse. If we started from nothing, right, before the Big Bang, some singularity, how have we ended up in a universe made of matter with basically no antimatter in it? We have all these conservation laws in physics that govern particle interactions. For instance, conservation of charge. If I start with no net charge and I create some particles, they also need to have a net charge of 0. So if the universe started with just energy, no particles, no net charge, why is it today that we have lots of electrons and really not many anti-electrons? We call these positrons. It's the only antiparticle that actually has its own name. So lots of electrons, not really many positrons. Where did they all go? Why do we have protons and not antiprotons? Why is there no anti-Earth? It's weird. So the Standard Model, right, which contains all of our known, right, particles and interactions, can't explain this discrepancy. There's nothing in it interaction-wise that if we start from the singularity at the start, we generate a bunch of particles, we generate matter and antimatter, and then we do the Standard Model. It says that everything should just annihilate and go away, and that clearly didn't happen because we're here today. So we cannot explain this discrepancy with the Standard Model. There has to be something else out there. Okay, so how does the Large Hadron Collider help us answer these questions? And why do we need such a large Hadron Collider? So the main type of particle, and I say main because it's really not the only one, the main thing we do, the LHC, is collide protons. These are tiny little bags of quarks and then the gluons that bind the quarks together. And if we want to study how particles interacted in the early universe, so maybe solving this sort of matter-antimatter asymmetry issue, we need to replicate that hot, dense state that existed before, for example, all of the antimatter went away. We need our protons to have enough energy that they can replicate the energy density of the early universe. So, I mean, in simpler words, we need to make the protons go really, really, really fast. You've heard of probably Einstein's relation E equals mc squared, right? That's energy and mass have some equivalence. It's equivalence between the particle's mass, it's just sitting there in its mass, and how much energy is actually held in it. And then there's some factors of c, the speed of light thrown in for good measure. This is right true for a particle sitting at rest. At the LHC, we're taking those protons and we're accelerating them to 99.9999, there's 6 of them, 99% of the speed of light. And that gives them a kinetic energy, energy of motion that's around 7,000 times greater than their rest mass. So we're giving them a lot more energy. And then we have to use the magic of particle interactions. Say magic here, there's nothing magic about it. We have to use particle interactions. And when high energy particles interact, they don't just bounce off each other like things do in our classical world and macroscopic universe. It's just not what happens at the particle level. They can actually completely disappear, and their energy can turn into the mass of new particles, right? So if I start with 2 protons, they don't have a very high mass. There's not that much energy, but if I make them go fast, I put lots more energy in, I can create particles that are way more massive than my protons, okay? It's not intuitive if you've never thought about it before. I like to bring this into like things that are macroscopic to completely emphasize that point. It's like if I threw 2 cupcakes together and got out in an Nanaimo bar, right? It's not how our world works at macroscopic levels. It's not what we encounter on a day-to-day basis. So if we collide 2 of these very fast protons together to create some heavy new particles, for instance, a Higgs boson, we do this fairly regularly now, we can do that. And the Higgs boson is actually 125 times heavier than a proton. So it's a really good thing we can do this. I wouldn't be able to discover the Higgs otherwise. Now, in order to accelerate these protons to their incredibly fast speeds, we need a very large accelerator for. Now, in order to achieve this, we actually need the Large Hadron Collider, and it has to be the size it is. That's why it's so big. It's 27 kilometers in circumference, okay? And it can simultaneously collide particles in 4 separate locations for 4 separate experiments around the ring. And if we want to see what happens in these collisions, we want to do an experiment with proton collisions, not just collide them and ignore it. That would be pretty boring. We need to take a picture of these interactions. And that's where our particle detectors come in. These are basically very giant, specialized cameras that take a snapshot of what happens when our protons collide. All right, so I'm a member of the ATLAS collaboration, and we use the ATLAS detector for this purpose. It's a 7,000-ton, 46-meter-long, 25-meter tall cylinder. That's round comparable to the size of a hockey rink. And it has 100 million different electronic channels that tell us where the particles produced in collisions travel. So if you collide some protons, you get a new particle. It says where it went and how much energy that particle had. So it allows us to reconstruct what actually went on in that collision. In order to do that, the detector has many different layers. It's kind of like an onion. Well, I think it's actually more like a leak. We use onion analogy a lot, but onions are spherical, and I just said the detector is a cylinder, so I think a leak is better. Now, the protons collide right in the middle, and the particles are then sprayed off in all sorts of different directions. Now, many particles are very, very short-lived. To emphasize this, I can give you a concrete example I gave to my students as a fun exercise this semester. I mean, I thought it was fun. I hope they did too. And that was to calculate how far, on average, does a Higgs boson travel before it decays. And if you work through the math, it's on the order of femtometers. Some of you might know what this means, some of you might not. So I'm gonna say it's tiny, 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 tiny. It's smaller than an atom, okay? It's definitely not something we can measure in the detector. For reference, the first element or like pixel in our detector is 33 millimeters away from the collision point, so it's distinctly bigger than an atom. So we don't see Higgs bosons. They decay before we can see them. We only see what they decay into. And this could be many different things. It's not just one thing. They can decay into basically any of the particles we talked about earlier, like quarks, electrons, muons, photons, and that's what we detect in the detector. Now, because these particles interact with the matter that makes up our detector in different ways, a photon does not interact with the detector material in the same way as a muon, we need different types of detector to actually be able to measure all these different particles. And that gives us our layers. There's different things in the layers so we can measure all of the different types of particles. And then what we do is we use the information gathered by each little piece of our detector, all 100, when I say 100 million electronic channels, to piece together what we think might have happened in that collision. So I hope you're starting to see how 6,000 people might be necessary to run these experiments. Right, so the ATLAS collaboration is basically a giant collaboration. We have 40 institutes from 40 countries, a lot more than 40 institutes, there's like 200 and something. And they are, we're spread all the way around the world. So there's 40 different countries, but we have 6,000 members and we come from many more. So we have about 100 different nationalities on the experiment. But ATLAS itself is our collaboration. We come together and work together under the banner of ATLAS. It doesn't employ anybody. CERN is, as the research facility, but it's an employer in the sense that it employs people to maintain the infrastructure and the space for ATLAS. There is a CERN ATLAS research group, but they're just an institutional member of the collaboration like any other, right? So we're just a management structure without actually being the employer. And this is quite unique. Now, our geographical diversity creates an incredibly unique collaborative culture as well, because no matter where we come from, we're coming together to work towards a common goal, really a common scientific goal, which is furthering understanding of the fundamental nature of our universe. And we all approach this goal with sort of differing ideas about what is important and how we'd like to achieve it. And the collaboration supports this with a sort of unique bottom-up self-organizational structure. So management might at some point suggest what could be done and what might be sort of motivated to do right now. Our data's here, please look at it. But it's rare that anyone would actually tell you what you should work on aside from perhaps your PhD supervisor. Now, around all of this freedom, ATLAS has this whole management structure to maintain any ability to get anything actually done. In the words of some of the many people who've actually used the ATLAS collaboration structure itself as their research subject, which has happened multiple times over the past few decades, I picked one phrase out, it's to maintain social and organizational cohesiveness. So I thought about this, what does this mean to me? Basically, it helps us minimize the number of wheels we reinvent. Now, the collaboration is overseen by an elected spokesperson, and underneath them there's 3 layers deep of management structure covering any areas from safety to computing to using the data for its intended purpose, which is physics analysis. This structure provides institutional guidance, but not intellectual direction. It doesn't tell us what to do, just how to do it, if it's what we choose to do. And as individual collaboration members, we can really choose to work on whatever we like within the collaboration. The only restriction is that at the end of the day, every publication is subject to our collaboration-wide review and scientific scrutiny. So you can't just look at some data and go, I think I see something new here and publish it behind the collaboration's back. That would be a no-no. But let me give you a concrete example. So if you came to start an analysis For example, on measuring the Higgs boson decaying to cupcakes, you would be structured within the Higgs boson to cake subgroup, within the Higgs boson food group. And when everyone in this thin sort of slice of the collaboration agrees your analysis is sound and well documented, your paper draft is then sent to collaboration-wide review. And one of the reasons we have to split up into this huge group structure, we have 7 different physics analysis groups and 33 of them underneath, little ones, is because there's people in charge of reviewing the analysis at every step along the way. And basically, we're responsible for reviewing the results coming out of the group, and if it's too big, it's not manageable. It has to be at a manageable scale. So to give you a sense of scale, when I was a subgroup convener, so that's at the lowest level, in the little management structure pyramid here, my little subgroup had 200 people working in it on 30 different analyses. That came out as like 30 different scientific publications. And these were all related to measurements of electroweak processes. That's processes dealing with, that are predicted by the standard model, basically things that have W and Z bosons in them. Now, I'm currently a member of the publications committee. So it's my job to read about 1 in 10 Atlas papers that are coming through the pipeline and do my very best to ensure they meet collaboration standards and don't break any of our guidelines. So there's a huge number of these different roles across the collaboration. I think we had a few novel ones I thought I'd share with you. They sort of mean something to me, but they won't to you, so it's kind of funny. We have a strip local support module mount coordinator, an isolation and fake forum coordinator, a metadata architect. Actually, there's multiple people in these positions. And my favorite that I actually just stumbled across when I was preparing for this talk is a fabrics coordinator. I really don't know what a fabrics coordinator fits in or what sort of fabric they coordinate. But I think that's just a testament to the size of our collaboration, that there can be so many things, many people that I'm sure are integral to our day-to-day operations that I have no idea about. Now, of course, there's a downside to having such a large management structure, and that is the number of meetings that spawn up. So our competitor experiment, also at the Large Hadron Collider, is the Compact Muon Solenoid, or CMS. And at one point, they were affectionately deemed the Continuous Meeting Society. In Atlas, it got so bad that we created a committee to reduce the number of meetings. They had some meetings, this is already off to a really bad start, and formally decided at the end that the only meeting they could cancel was their own. Such is life. So while I can't say that our management structure is like the most efficient system, for some baffling reason, it does work. All in all, most of all these roles within Atlas are management positions with no extra pay, no actual authority, a lot more work, and I think for better or for worse, they're all filled by physicists. It still works. So we have the Large Hadron Collider, can collide us some protons, we have a detector that can capture what happens after, and we have a management structure to ensure that everything is up and operational. So now we can deliver some beams. I'm gonna need a little volunteer for this next part. Maybe somebody with an accurate throw, somebody who plays baseball? Yes. All right, let's bring this. All right, what's your name?
I'm Andrew.
All right, Andrew, thanks for volunteering. Okay, so CERN wouldn't lend me a particle accelerator, so we're going to have to improvise. And Andrew here is going to be our particle, or our accelerator, maybe both. So he can have a ball, and I'm going to be the detector. I'm gonna need my bin. All right. So at the LHC, protons collide head-on. But you don't want to watch us try to do that for the next 20 minutes. So for demonstration purposes, this is going to be what we call a fixed target experiment. That's where one moving particle hits a target. I guess that's me. So if Andrew throws me one ball, please not too hard. I only have one hand, so if I can catch it. No. Normally I'd catch that. I have a mic in my hand. This one is red, potentially a dark matter candidate. Yeah, let's save that in our data storage. Okay, so that was far too easy, and not at all what the LHC does. It certainly doesn't give you one collision and then wait for you to figure out what you want to do with it. So we're gonna get some protons actually in a slow, steady stream. All right, so here's your protons, your particles. We get them in a slow, steady stream. I'm gonna have to put this back or I'm never gonna be able to catch anything. Okay, slowly. Okay, so I don't really have time to check each proton or each collision if it's interesting, but I could save them into data storage for further analysis. But that's still not really super accurate for what the LHC does. The protons actually come much, much more rapidly. So let's see if we can handle that. All right, so if you could just collect these back, that would be very helpful. So the key here is that this is more accurate for what the LHC does, and it just keeps going. It doesn't wait for you. So I can't deal with all the incoming protons fast enough. I probably missed half of the interesting events that happened. And on top of that, my data storage was still filling up pretty quick, but most of it was probably garbage. It wasn't very interesting. It wasn't the fun stuff we want, like our dark matter. And it's stuff that any analysis would sort of immediately throw away. So why do we want to keep it? We don't. What we need here is a filter that can remove the stuff we don't want. We call that a trigger. This is something that triggers the processing and saving of a collision event. Specifically, what we want here is a hardware trigger, because my software, or maybe my reflexes, that'll be my software, can't inspect the protons fast enough to make decisions. So we're going to try this again with a foam board only sending through or triggering the good protons. This is going to act as our hardware trigger to lower the rate of incoming objects. The software trigger, me, has time to react and think. So, let's see, I can't do it at the same time. We're going to throw some balls over at the same rate, and we'll see what happens now. Give me a second to set up. That's what the giant foam is for. All right, it's my shield. You can take these ones back, too. It's entertaining. It's really effective. Oh, I missed. That was gone. Ah, right into the storage. I should do this. Got one. You probably don't want to watch this forever. So basically what we're doing is we're reducing the rate in so that basically the data storage is more manageable. I can make decisions on a more manageable scale. I don't have to deal with 40 coming in each second. I just have to deal with like 1 or 2. And honestly, the fact that some of them miss is accurate, right? We always have to make a few sacrifices in our collisions. So let's all thank Andrew, I think, who has a bright future ahead of him as a particle accelerator. And we can relate this a little back to the LHC. So the LHC isn't just tossing us protons, right? This is like, the scale is far beyond what I can demonstrate in front of you. The LHC actually collides bunches of protons with bunches of protons. It's actually 100 billion protons into 100 billion protons, all compressed into a really tiny bunch. And they do this 40 million times per second. This creates an incredibly high rate of collisions inside the detector, and we have to figure out if an event is worth keeping really fast, because the next one's coming 25 nanoseconds later. And if we don't, we're going to rapidly accumulate a backlog of maybe events, like I just had scattered all over the floor before. Now, the speed of processing is one aspect. We can go really fast, but there's another thing to note here. If we want to study these events, to search for new particles, we need to keep the data in storage. The detector information from each collision, from one collision in the detector, is around 1 megabyte. So with no filtering, we'd end up with fill up like a 31 terabyte laptops per second. That is unsustainable, right? So we have to filter things down. The other thing to note is, okay, if this fill up a terabyte per second, or 30 terabytes per second, why do we just lower the rate? That would be easier, wouldn't it? I agree, it would be simpler. But most of the events aren't interesting. The only reason we collide so many protons into so many protons so frequently is that some of the awesome types of events that we want to study are incredibly rare. So rare that like even with these high collision rates, like the rate of a Higgs boson decaying to 2 muons, that happens about once a day. And we don't take data for a billion years, so we want enough events to study. We need to collect all of them. We need as many as we can get. This is really what I call sort of the double-edged sword of data taking. We want the LHC to give us lots of collisions, but then we have to cope with the huge data rates. If we had fewer collisions, we could cope with the rate, but there would be a much lower chance of actually discovering anything interesting. I'm putting all this together. Basically, it means that we're constantly running right at the edge of our capabilities. And really, we need to really rapidly figure out which collisions are interesting enough to consider saving. Now, we don't have foam screens inside our detectors. I mean, the holes would have to be really way too small. Our hardware triggers are actually electronics, like we have in computers, except they're chips that are designed for one very specific purpose. If you're somebody who knows, I'm talking about ASICs and FPGAs. If not, what I mean is we have custom chips that allow them to be very fast at a few predetermined tasks, such as deciding if there is one high energy particle and then deposit in one part of the detector, or if like two energy deposits look like they might have come from the decay of a Higgs boson. This hardware trigger system takes the incoming 40 million collisions per second and lowers it to 100,000. So it selects out 100,000 of those 40 million per second. That's the maximum rate that our software trigger can manage. So we go beyond that, the software trigger just huddles on the floor and cries. Right? So we can't actually go any higher than that. And with the software trigger, then we have a lower weight. We can rerun basically many advanced algorithms, just software, to see if an event is actually worth saving or not. Not just it fit through the hole, but it fit through the hole and it was red and it was really spherical, that sort of thing. And we have to do this just in time for the next collision event to arrive. Now, when I was a postdoc, I actually spent a significant amount of my time making sure our triggers, that this one, I have to show you this one because I spent time making it. Looked over here. Or for instance, far more specific ones. We have a pineapple trigger. There's a pineapple in here. I don't think it got thrown. We would never be able to get it through that hole. But we had to make sure that our triggers like that were the correct ones. So we didn't make a mistake in what we cut out. And we had to make sure they were running at the correct rates. There wasn't some mistake in them. They were configured in a way that didn't give too much of data through, because then the software trigger would fall over and die. And that was a very important piece of making sure that we got our data taking done. And the LHC, right, if it collides protons faster than our electronics can handle them, that's where we need to start thinking about what we're selecting. So much of this time, as a trigger expert, I spent in sort of week-long on-call shifts, so we could provide dedicated support to all the issues, I say all, any possible issues that might arise, which was basically anything, everything. And in this time, I learned that there are a few rules of the LHC. First collisions always happen over Easter weekend. That actually wasn't true. I think we just heard we did first collisions this year, so for once, 2025 has already happened. And that's regardless of what the schedule said. It was true many years in a row. The LHC is always going to find a way to deliver collisions that will break your data-taking setup. And this is whether or not they over-deliver. They go, hey, we actually figured it out. We can give you more beam. Or less. They go, oh, we have some problem. We have to reduce the rate. We're going to change how we put the protons in the system just in the exact way that breaks your system. And inevitably, all of these changes that happen occur at 4 in the morning. It's just reality. Now, these people that maintain the detector, they work shifts in the control room or on call and debug all of the issues that we find along the way. They're the same people that analyze the data we record. So each person contributes their own unique area of expertise, ensuring that we record this high quality data. And for the most part, Atlas shares one big data set. So it's not like I go to CERN, I collect my data set, and then I do my research with it. We all share the same data set. And it's really more with all sorts of, it has like 1,000 different trigger selections in it. So it's really a big grab bag of anything and everything we could possibly think to save to make sure we didn't miss some exciting new particles. And I think once we've got that grab bag of events, that's when the fun starts. Now, as a collaboration, Atlas, we've published over 1,300 papers, each with our 18 pages of author list, discovered the Higgs boson, recently observed quantum entanglement in the heaviest quarks, the top quark, and we've searched basically in every corner for supersymmetry. So do let me know if you find it hiding out somewhere. It is a slippery one. We're still looking. Now, the Nobel Prize Committee has a sort of arbitrary, antiquated agreement that it can only be awarded to a maximum of 3 people. And that's only science that's really done by small numbers of people is eligible. So for the Higgs boson discovery, the Nobel Prize went deservingly, not wrong, to the theorists who predicted the boson's existence. And none of us take this personally, it's fine. I only bring this up because we actually have won other prizes, and amongst them just this week. So on Monday, it was announced that we just won the Breakthrough Prize in Fundamental Physics, which is pretty neat. And this was awarded to all of the main LHC experiments. This is a total of 13,000 physicists. It's a very long page of people. That's pretty cool. So Atlas collectively won around $1.4 million, or $230 per collaboration member. So rather than mailing us all checks, this goes into a scholarship fund for graduate students to spend time at CERN. So they don't go through the process of spending it out. And it goes to a good cause. But in any case, I hope taught you a bit about how the Atlas collaboration works and a bit about particle physics. And I'd be happy to take any questions. There's lots of frantically waving hands at the back. I can't see them because of the lights. He gets to choose.
Okay, who wants the first question? Let's start right in the back.
Yeah. So I saw some headlines recently. I didn't really read the article, but it was something about CERN building a larger Hadron Collider. Is that true? And what would that facility be looking for?
Yeah, so this is talking about the Future Circular Collider, FCC. And basically, the LHC program, so this 27-kilometer collider, ends in 2041. That's the end of our data taking, and we'll be done. So then the question is, what do we do next? And we sort of, the big leaps come from increases in energy. So you can't do that with a 27-kilometer ring. We don't have the technology. You need something called Bremsstrahlung radiation. You need a bigger collider that has a smaller bending radius if we're going to make our particles go faster or have higher energy collisions. So this is where the idea of the Future Circular Collider comes in, is around 100 kilometers around. And it would have new experiments then at points along the ring that would have collisions in the same way that the LHC does. It's still under discussion. It's not something that's approved or funded. CERN would like to have it, but that's the stage we're at now.
Yeah, I'm just wondering, are Elon Musk's cuts having any impact on funding in the LHC world?
Not that I've heard of yet. We're trying to stay under the radar.
Kind of a strange question. Thank you for your excellent talk. You started at the beginning talking about space and very, very large distances, and most of your work is dealing with the smallest distances possible. Where do we fit in on that spectrum of the very big and the very small? Human existence of meters, tens of meters. Where are we?
So yeah, the scale of very tiny to very large universal scales, where do we fit in as humanity? It's an interesting question because, right, we think, when I think of like fundamental particles, these are tiny distances, and that somehow doesn't seem relevant to human life. But I think it is, right? The electrical impulses in our brain are electrical because there's electrons, right? There's particles, there are, I'm not a biologist, I don't want to say anything wrong, this is the problem, as a scientist. But like there are, processes that deal with fundamental physics that are integral to human life, right? Things to deal with quantization with photons are important for instance, photosynthesis. Atomic transitions, and you have fluorescence. This is, dealing with fundamental particle interactions. So in that sense, it matters despite our macroscopic scale. It actually affects us. On the other hand, the fact, the scale of the universe, maybe not the universe scale, but the solar system matters to life as well, right? We're where we are today, an inhabitable planet, because there's a sun at the right distance. So I think it all works together. Maybe that answers your question. The question is, how does the Higgs boson give other particles mass? This is a complicated one that I definitely glossed over. So at really high energies, there's something called unification of our electromagnetic force and our weak force. And in order for the weak bosons, the W and Z bosons, to have any mass in the standard model, we need something to break that symmetry, to break that unification of the force, so that we end up with a massless photon. Photons have no mass, and massive W and Z bosons. And that, if you put that Higgs boson into the math and work through it, what we call a mass term, there's something like how we give particles mass in our equations comes out. So that's it's been basically completely integral to the system. We don't have the Higgs boson in our math. We can't put mass in for these particles. And we measure them. We know they have mass. The other particles are a little easier. You can just sort of write down terms for it. But the W and Z are the most important part. Does that answer your question?
Right in the back at the bar, please.
Hi, thank you for your. In the beginning, you mentioned how when two electrons communicated with them, so how they repel, was they would throw photons at each other. If I'm recalling correctly. If I'm saying it correctly again, any interaction between particles has to happen in some sort of field, right? So, and then that field has to carry carrier particles. And then you mentioned like 15 different particles, and there's like collisions that you were observing at CERN with Atlas. My question is, with all the fundamental and non-fundamental particles and their interactions, do they happen in the same field? So do they communicate? Do they communicate in the same field, and then do they use the same carrier particle to communicate?
Yeah, so this is the question is we have all these particles in the standard model and these different, they all communicate in the same field or different fields, and it's actually a really interesting question because it's yes and no. Some particles interact with some fields and some interact with others. So for instance, the electron interacts with the electromagnetic force and also the weak force. So it'll interact with the weak field and electromagnetic field. Quarks interact with a strong force. They have a charge under the strong force we call color, but they also have charge, right? They form a proton. There's charge in them, so they interact with the electromagnetic force and the weak force. Electrons, for instance, they don't interact with a strong force, right? Otherwise, they'd probably fall into the proton or something in an atom. But yeah, so their different particles are basically we say are charged under different interactions. Different particles interact with different fields, and all of that structure is built into the standard model because it fits the phenomena that we observe.
How, if at all, are advancements in AI going to change the research?
How, if at all, are advancements in AI going to change our research? So this is also a good question. I didn't talk about it, but I was tempted to. So AI has become a thing that many people are hearing about now, right? And we've been using what we call machine learning, now we call AI, in our research for decades. Right? It helps us be able to disentangle things that look super similar in the detector so that we can say, yeah, we have a Higgs boson, or we don't, or this is an electron, this is a photon. How do we tell them apart? AI helps us do these things. In what we're thinking of AI these days is generally large language models, right, with ChatGPT and such. And this has another benefit, is if you're in a big collaboration, you end up with very fragmented documentation and code base. And it's very hard to keep track of. And you can stick all this in an AI. You can stick mailing list history in an AI with all the questions. We use Mattermost, like a Slack messaging service. You can stick all of those discussions into a language model and have it answer questions for you. So this is actually something being worked on as well. So we use kind of both types of AI. It doesn't really work great yet, but it is something we're developing because it has great promise.
All right, in the back there, please.
First of all, thank you for coming and giving this talk. I was really wondering how applied researchers are using this data and this discoveries that are being made in the field of like energy and that kind of development that we're seeing.
The question is, how are applied researchers using the outcomes basically of the research we get at the LHC? And the answer is they're not. So this is what we call fundamental physics or fundamental science. There's no immediate obvious application. And that's okay, because a lot of things used to be fundamental science. The invention of electricity was not because we thought, let's do something really practical. It was because they happened to see something. Some scientists went, or physicists went, yeah, okay, something happened, published it, and carried on with their life. And somebody else went, hey, that could be kind of useful. And it was the same with the cathode ray tube, right? This is J.J. Thomson throwing electrons and saw that they sort of flashed on a screen. Went, okay, that's some science, carry on. And somebody else went, hey, I can make a television out of that. Right? So there are leaps that can happen. We don't know what they are, but we never know what, not never, often do not know what they are at the time. And we sort of have to look, or we're never going to make those advancements. But I can't say what they'll be yet.
The fields we learn about in high school are gravitational field and electric field, and they vary as the inverse square. Is that true of the other fields as well?
It is not. That's why they're different.
Yes, thank
Yeah,
you.
so they're not infinite range in the same way. There's sort of difference. So the weak force, Gravity is we don't know how to fit gravity into the standard model. That's a whole nother problem. You have to invite somebody else to talk about that. Electromagnetic force, again, is infinite range. It has a massless mediator. The strong force would be, but because it's so strong, other effects come in and keep it short range. And the weak force has a massive particle that mediates it, and that affects basically how long the range can be. It's also a short range force. They're also more complicated to explain, so we don't tend to teach them in school.
Okay, I see 2 questions in the back. Maybe we start on the right and then to the left. I don't know which one was first, but let's go this order.
I was wondering if the Large Hadron Collider provides any basis for string theory.
Does the Large Hadron Collider provide any basis for string theory? No. String theory is novel. It might be there, but it's not. Its big problem is that it's not really testable. And there are some aspects of it, like supersymmetry, that could be related to string theory, that do predict particles that we look for, we haven't observed. But in and of itself, discovering one of those particles wouldn't prove string theory. It's more the other way around.
First of all, thank you for your talk. I have a couple of questions. First of all, how does the W and Z bosons, how do they govern nuclear decay? And why does the Higgs boson particle decay so quickly?
All right, so how does the W and Z govern nuclear decay? And this is in the same way, I suppose, what do I say? So in nuclear decay, I'll just describe what happens. In nuclear decay, or beta decay, a neutron, this is 3 quarks, down, down, up, turns into a proton in the nucleus, and you get out an electron, right? This is what you probably learn in school. Conserved charge, we're all good. So it's not actually what's going on at the particle level. What happens is one of the quarks in the neutron emits a W boson, and that W boson then decays into an electron and an electron antineutrino. So there's the whole antineutrino part we definitely gloss. Is one of the things we gloss over in school. We don't tell people that in beta decay until they get to university. We don't tell them there's that W boson in between, really, but it's there. And then the other one is, why does the Higgs boson decay so fast? And this is basically because it has so many options of things it can decay into. So it has infinite choice. It can just go really quickly into one of those. More or less what happens without explaining the math.
All right, there's one more on the back, and then we move over here.
So I just want to ask, do you believe in the existence of the graviton? And if so, how long, if ever, do you believe humanity will discover it?
Right, do I believe in the existence of the graviton? And if I do, how long it'll take for humanity to discover it? So I don't believe or not believe in particles because I'm a physicist, and that's just not what we do. I'm happy to look for it. But it's not, my belief doesn't affect that, right? Do I think it'll exist? It's possible, right? It's also possible that it does exist, but it's not in a regime where it's observable. It's not maybe something we could discover with the technology we can foresee today. So hopefully that answers your question.
One in the front here? Yes, please.
Yeah, is there a predictable benefit for a larger collider?
Is there a predictable benefit for a larger collider? This is a fascinating question. I was thinking what I would say. Somebody brought all this up. I was like, should I just ignore it? So I myself, I can say personally, this isn't being recorded, isn't it?
It actually is.
It is. Be careful what I say. There are reasons to build a big collider, right? We have mysteries in the universe we do not have the answer to. Is there one exact solid reason, like we had for the LHC, the discovery of the Higgs, to build the collider? No, not right now. But if we don't start, we'll never have it. And that's a problem, because you sort of need to maintain expertise in a field. And if you wait 20 years, everybody's gone. People find different jobs. There's nobody to train students, and you don't know how to build a collider anymore. So we can't necessarily wait 20 years for that theory to come up and then go, yeah, it's time to build a collider. And also, they take a long time to build.
All right in the front.
So I have 2 questions. Question number 1 is why does it stop in 2041? What is happening in 2041 that it stops? And then question number 2 is totally unrelated. Does your center accept co-op students? How do you train the younger generation to come and work or learn about your?
Sure. So why do we stop in 2041? It's sort of a date that's got pushed back. I think it used to be a nice round number. But the reason is we're at a given energy. We're colliding at a given energy. And at some point, we've collected so much data at that energy that everything else is just like marginal gains. You don't have the same like cost-benefit ratio that comes out. It's not really worth it anymore. It's better to analyze the data best you can and focus on something new. And how do we train people? Well, I mean, I have 4 undergraduate students working for me this summer. One of them is a co-op student. Probably another one will make it a co-op term. And it starts there. You can work up. There are programs at, for instance, Triumph is a Canadian lab in Vancouver that hires summer students. We have Snow Lab in Sudbury, Ontario, that does neutrino physics. They hire summer students. And we sort of train them from there up. We also give courses in particle physics in our program.
All right, let's stay on the left.
Could you explain supersymmetry? What is that?
So supersymmetry is a model where every particle has a superpartner. They have fun names, like an up. You have to put an S in front of the name of a fermion or like a quark. So you call it an up quark is a sup partner, so supersymmetric partner. The top quark has a stop partner, and electrons are selectrons. Bosons turn. You put an eno at the end, so you get a W, a weno. Or the gravitino, if you feel like you're gravitons. So this is the name. I always think they're kind of cute. But the idea is that like every type of particle has a partner that's the other type. And I didn't talk about fermions and bosons, but the 2 different fundamental sort of types of particles. And supersymmetry says that if you have like an up quark, which is a fermion, it has a partner that's a boson. And nominally, they're the same mass, but that doesn't actually, we looked for that, it doesn't exist. So then there's all sorts of other ways you can have the theory so they're not like exactly symmetric, and you have some sort of splitting between that. And then you look for it in 1,000 places, you still don't find it, you make it even farther away, and you keep looking. But that's the general idea. Basically, physicists like things to be pretty and symmetric, so it's a nice theory.
Quite unnatural, well, at least from what we learned, it's quite unnatural for forces to just cut off instantly. Usually there has to be some counteracting force for this to happen. So, hypothetically, if you were to isolate the strong force, will it still cut off?
Yeah. So I can't explain. This is actually one other thing. I think of all these questions you're asking. I'm just going to gloss over that. Nobody will care. You do. So the strong force is so strong that when you try to pull particles apart, if there's 2 quarks really far up, you try to make them far apart, so the strong force is binding them. It's so strong that it'll actually break and will create new quarks. It'll pull quarks out of the vacuum to like avoid having to get pulled apart. It's like a spring that's like incredibly strong, and it can't be broken or can't be stretched anymore, so that it like creates 2 new particles in springs. So that's what happens. It doesn't just cut off. It gets really, it just drops or gets so strong, keeps increasing in strength that it sort of changes how it interacts. Okay? It's something called confinement, right? We do not have free quarks flying around. It's not possible. Or free gluons. It's just not something that's physical in the theory. Can you contact me? You can. I prefer physics students because I have a lot of them contacting me already. I can't promise to give you detailed answers because I only have so much time. But yeah, for sure, feel free to email me.
Just more of a personal question. Where would you like to see yourself in the Atlas program next? Like right now you're in publications, but like where's the sweet spot? Where do you want to be?
Yeah, so I've kind of thought about this. It's actually really hard as a professor with like teaching responsibilities to be super involved in terms of management. So this involves sorts of negotiations and course releases and things like this that, you know, it's money. It's a money question for the university. So it's not something at this point that I think I foresee myself doing. There's also a lot of, you know, not so fun stuff that comes along with being in charge. I've done some time in these positions, been asked to do a few more and said, you know, maybe not. Maybe I'll feel differently in 10 years after I'm more settled into, you know, what it means to be research faculty and have myself tenure and everything like that. But I'm not seeking management. It's not where I see necessarily the most value.
Is it all management? Like, is
Oh, so in terms of, yeah, management, like, Positions, yes. Otherwise, I mean, what I actively do is not just read papers. I do analysis of data. I look for basically like multi-boson interactions, like lots of W's and Z's. I search for these or measure these processes. And I have multiple groups I work with who are doing that, and students and postdocs. But yeah, in terms of roles and sort of status, that's not my goal.
What type of work is coming out of Sudbury?
What type of work is coming out of Sudbury? So Sudbury has, maybe somebody knows the name of the mine. I don't remember. Yeah, so there's a big mine. Sorry, it's hard to hear up here. And inside of it, there's like active mining on one side, and you go all the way down, and there's another side where they're done, which we've put lots of neutrino and dark matter experiments in. So they don't have like any collider down there, but they're looking for like atmospheric particles or dark matter that could be interacting in like tanks of xenon and stuff. They're really cool. Suggest you look it up. There's some great info on their website. It's called Snow Lab is the lab, but it's not what I work on.
Was a question in the back?
Yeah, what makes a strong force so attractive that it overcomes proton repulsion?
What makes it so attractive? I'm going to flip that question around. If it weren't attractive, nothing would hold the proton together. And that would be a problem and we wouldn't be here. Right? So nothing's made the Standard Model the way it is as far as we know. I mean, there's different sort of philosophies behind this. It's more like a philosophy of science question. But the way I think of it is we live in a universe where the parameters of the Standard Model are such that they support us. They support bound states and protons and neutrons and atoms and us, right? And if the parameters of the Standard Model maybe in a different universe had worked out differently, there wouldn't be that. Right? So maybe it tried lots of times. There's lots of singularities, lots of universes, if you have many worlds, theories, if you support that, for instance. Maybe there were lots of trials. This is the one that worked. Or maybe many of them work, and there's like slightly different parameters out there with slightly different shaped people. I don't know.
All right. Are there more questions? I'm going to make a last call. Okay. I don't see any. That's chance. There's one in the back. Alrighty.
This is an extremely long shot, but I know someone who works with Atlas. Do you know Are Strandli, like a Norwegian scientist?
Sorry, can you say the name again?
Are Strandli.
Can you say it in like how I might say it?
Are Strandli.
I don't think so. I know people who work in Norway. I know people who work in Oslo, but I don't know the name. What's they have student, a faculty?
Not University of Oslo, but like university.
Yeah.
I knew it was a long shot.
Yeah, no. It's probably somebody I've come across before, but there's a lot of us. Yeah.
Okay, last call. All right, I'm scanning the room.
You know everything there is to know about fundamental physics.
All right. All right, there.
Somebody realized they don't. I don't actually know. I'm sure they do. We give tours at CERN. They probably give tours at Sudbury. I'm not sure if you can go underground. There's like a clean room system to make sure you don't contaminate stuff. But for sure up top, there's going to be visitor centers and rooms. They have a great outreach program. Yeah.
Oh, okay. Oh, very well.
There's more.
My question is related with, in the Lagrangian of the Standard Model, the neutrino is massless, but when we analyze experiments, the neutrino oscillates, so it should have a small mass, right? So what's the explanation of it?
Right, so this is one of the problems of the Standard Model I didn't mention. So neutrinos in the Standard Model are massless. And this is the Standard Model Lagrangian. The equation that you write down for the Standard Model has no mass. But we know neutrinos do have mass. So what gives? Basically, we don't know the mechanism by which neutrinos have mass. We know that they do, but we don't know how it actually works. There are multiple ways this can happen that are equally valid at this moment. And they fit into the Standard Model. We just don't know which one it is. So we don't know which one to put in. And when we do know, we'll put it in. One of them is called a seesaw model. Another one's, there's Majorana neutrinos. I don't know if it's the same one. It's not my field. Yeah, seesaw is I think one of the common ones. You can look up seesaw or Majorana neutrinos.
Okay, very, 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 very last chance to ask a very last question. I guess, okay. Set, all right. Okay, thanks. Okay, let's thank Heather again. Thank you so much. Great. Thank you. All right. Well, thanks everybody for coming. I mean, yeah, thank you for being here. This is amazing that we attract so many people here for this Café Scientifique. And yeah, I hope to see many of you back in September when we restart. And yeah, feel free to reach out to us if there's anything specific of the science in UVic you would like to see presented here. Well, thank you, everybody.
Thanks for coming.
No, you can't say everything.
Thank you. Where did that one go?
There's a filter right there.
Yeah.